In today's video, we're going to look at several special types of matrices. There are three in particular that will be of importance throughout the rest of the semester. They are the square matrix, the identity matrix, and invertible matrices. We start by defining several of these special types of matrices. First, an n by n matrix, so a matrix that has the same number of rows as columns, is known as a square matrix. A square matrix such that aij equals 0 whenever a is not equal to j. This is known as a diagonal matrix. A square matrix such that aij is equal to 0 whenever I is greater than j is known, as upper triangular. Conversely, a square matrix such that aij is equal to 0 whenever I is less than j is called lower triangular. A diagonal matrix such that aii is equal to c for all I is known as a scalar matrix. Right, in other words, a scalar matrix is a diagonal matrix such that all of the elements on the diagonal are the same. And finally, a diagonal matrix such that aii is equal to 1 for all I is the identity matrix. Right, so we denote identity matrix as I sub n. This is the n by n identity matrix. Right, so if we were to write, let's say, oh, why is that? Let me fix that thickness. All right, if we were to write I3, that would mean the 3 by 3 identity matrix. This graphic not only serves as examples for these types of matrices, but also show how these matrices are kind of related, right? If we look, outside we have just different types of matrices. Let's start with the inside. Identity matrix. This is the 3 by 3 identity matrix, right? You can see that all the elements of the main diagonal are 1. Everywhere else is 0. And we can see that the identity matrix is actually a special case of a scalar matrix. So identity matrix is a scalar matrix. The 0 matrix is a scalar matrix. Right? The main diagonals are the same, 0. Never said up here that C had to be non-zero. This is also a scalar matrix, right? 6, 6, 6 on the main diagonal and 0 everywhere else. But scalar matrices are a special case of the diagonal matrix. And you can see that the only non-zero entries are on the diagonal. Again, this is a diagonal matrix because the non-zero entry 3 is on the main diagonal, and everything else is 0. Right, then we have upper triangular over here on the left. Right? So everything, all entries below the main diagonal have to be 0 to be upper triangular. Right? As you can see, we can kind of draw this. Let's make sure this is proper thickness. It wasn't. As sort of a triangle that points upwards for the quote-unquote non-zero entries, right? But you can have 0 entries up here. As long as everything below that triangle is 0, then it's upper triangular. Likewise, with lower triangular, we can draw a right triangle that's kind of pointing downwards. Everything above that has to be 0 to be lower triangular. And finally, square matrices, matrices that are just same number of rows as columns. And notice that all of these special matrix types that we've studied are all special cases of a square matrix. Next, let's look at two other types of matrices. So we say that a matrix A is symmetric if A transpose is equal to A. So if the transpose of the matrix is the same as the original matrix, that matrix is said to be symmetric. If instead A transpose is equal to negative A, we say that A is skew symmetric. Right, and down here we have two examples. This is a symmetric matrix, right? Because if we take a look at A transpose, remember, to take the transpose of a matrix, rows become columns, columns become rows, so the first column would be the first row of A, 1, 2, 3. Second column is the second row of A, 2, 4, 5. And then the third column is the third row of A, 3, 5, 6. And if we now compare this to the original matrix A, right? First row, 1, 2, 3. First row, 1, 2, 3. Second row, 2, 4, 5. Second row, 2, 4, 5. Third row, 3, 5, 6. Third row, 3, 5, 6. These two matrices are the same. Right? Likewise, down here, if we were to find B transpose, right, first column would be 0, 2, 3. Second column would be negative 2, 0, negative 4. Third column would be negative 3, 4, 0. If we now compare this to B, first row of B transpose, 0, negative 2, negative 3. First row of B is 0, 2, 3. They are negatives of each other. Second row is 2, 0, 4. Second row here, negative 2, 0, negative 4. Again, they are negatives. Third row, 3, negative 4, 0. Over at B, negative 3, 4, 0. Again, they are negatives. So B transpose is the negative of B. Hence, it is skew symmetric. If we start out with an M by N matrix A, represented as Aij, and then cross out some, but not all of its rows and or columns, we obtain what's known as a submatrix of A. Right? As an example, let's take A, this 3 by 4 matrix, 1, 2, 3, 4, negative 2, 4, negative 3, 5, and 3, 0, 5, negative 3. Cross out the second row and third column. Right, let's do that in blue. Right, so we're crossing out the second row. Cross out the third column. What we are left with, right, is the matrix 1, 2, 4 and 3, 0, negative 3, a 2 by 3 matrix. This is a submatrix of A. Why? Because we got it from A simply by crossing out row 2 in column 3. Now we call an array that contains individual matrices a partitioned, sorry, wrong color, a partitioned matrix, right? So really, a partition matrix is just a matrix of matrices, right? So here's an example. We have this 4 by 5 matrix A right here. What we can do is essentially divide this, right? As you can see here, right? So we divided at column 3 and then again after row 2, right? This is a partitioned matrix of A. Notice it contains 4 matrices. It contains 2 by 3 matrices, this one up here, this one down here, and then 2 by 2 matrices, this one up here and this one down here. We could also partition it as we do down here, right? After the second column, after the fourth column, and after the second row. This is also a partition matrix of A. Notice here we have a matrix containing 6 matrices this time. We have 4 2 by 2 matrices and 2 2 by 1 matrices. Right? We have, here's our first 2 by 2, second 2 by 2, third 2 by 2, fourth 2 by 2, and then our 2 2 by 1 matrices, also known as a column matrix. An n by n matrix A is called nonsingular or invertible if there exists an n by n matrix B such that A times B equals B times A equals IN. Such a B is called an inverse of A. If no such matrix B exists, we say that A is singular or non-invertible. So if, as in example 4, we're asked to verify that one matrix is an inverse of another, right? So to verify that B is an inverse of A, what we have to do is show this right here, right? We have to show that if we take A times B, we get the identity matrix. And if we take B times A, we also get the identity matrix. For this example, what we want to do is we want to show that both orders of multiplication result in the 2 by 2 identity. That is the matrix 1, 0, 0, 1. Let's first take A times B. Right, so this is 2, 3, 2, 2 times negative 1, 3 halves, 1, negative 1. Right, so first entry, remember, when we multiply matrices, we're looking at the 1, 1 entry, so we want first row of the first matrix, first column of the second matrix. 2 times negative 1 is negative 2, plus 3 times 1. Right, the 1, 2 entry, we're going to have 2 times 3 halves, plus 3 times negative 1. 2, 1 entry, we're going to have 2 times negative 1, plus 2 times 1. And the 2, 2 entry, we're going to have 2 times 3 halves, plus 2 times negative 1. When you do the arithmetic, you see we get the identity. So A times B worked out. Now for B times A. Now it's negative 1, 3 halves, 1, negative 1, times 2, 3, 2, 2. we're going to have negative 1 times 2 plus 3 halves times 2. Then we will have negative 1 times 3 plus 3 halves times 2. Then we will have 1 times 2 plus negative 1 times 2. Let me write that lower down like that. There we go. Then we will have 1 times 3 plus negative 1 times 2. And again, do out the arithmetic, we get the identity matrix. Therefore, we can conclude that B is an inverse of A. We are now going to look at several properties of non-singular matrices. First, the inverse of a matrix, if it exists, is unique. So to prove this, we suppose that we have two matrices, B and C, that are both inverses of a matrix A. The idea is to show that actually B and C have to be the same. Right? Well, if B and C are matrices, are inverses, then we know that A times B is B times A, which is the identity matrix. And also that A times C is equal to C times A, also the identity matrix. Therefore, what we're going to have, B, well, B can be written as B times IN. Right? Any matrix times the identity is itself. But we just said the identity is A times B. I'm sorry, A times C, rather. We can regroup matrix multiplication as long as we don't change the order. So we can write this as B times A, then times C. But B times A is the identity matrix. And the identity matrix times any matrix is the matrix itself. So in this case, IN times C is equal to C. Well, we just showed then that B is equal to C. That is what we wanted to show. So, if a matrix has an inverse, that inverse is unique, meaning it is the only inverse. In other words, if we come back up here, if a matrix A has a matrix B such that A times B equals B times A equals I, then that is the only matrix B that satisfies that property. Next, let's look at Theorem 2, which says if A and B are both non-singular n by n matrices, then A times B is non-singular. And the inverse of A times B is the inverse of B times the inverse of A. Right? In other words, the product of two invertible matrices is itself invertible. And specifically, to find that inverse, you take the inverse of each matrix and flip the order of multiplication. To prove this, what we're going to do is we are going to prove that these two matrices are inverses. Right? So we'll prove that the inverse of AB is B inverse times A inverse. This will prove that AB is non-singular because we found the inverse, and it also proves what the inverse is. So start by doing AB times B inverse A inverse. take away all the parentheses. We have A, B, B inverse, A inverse. Remember, as long as we do not change the order, the grouping doesn't matter. So we can write this, A times B inverse, then times A inverse. Since B is non-singular, B times B inverse is guaranteed to be the identity, so we have A times IN times A inverse. Again, grouping doesn't matter, so we can group A with the identity matrix, which is, of course, just A. And again, since A is invertible, non-singular, that product is just the identity. So the product of AB and B inverse A inverse gives you the identity matrix. Well, in a similar fashion, we can find that B inverse A inverse times AB is also equal to the identity. Right? Therefore, we've just shown that A times B has an inverse. So it is non-singular. And that inverse is B inverse times A inverse. Now, as a consequence of this theorem, in other words, as a direct corollary, if we have R n by n non-singular matrices, like A1, A2 up through AR, then their product is non-singular. And its inverse is AR inverse times AR minus 1 inverse times so on and so forth times A1 inverse. In other words, if you take the product of non-singular matrices, it has an inverse. And its inverse is found by taking the inverse of each matrix and writing the product in opposite order. Theorem 3, if A is a non-singular matrix, then A inverse is also non-singular, and A inverse inverse is the original matrix. This proof will be left as an exercise. It's a fairly straightforward exercise. And finally, theorem number 4. If A is a non-singular matrix, then so is its transpose. And the inverse of the transpose is the transpose of the inverse. We're going to prove this the same way we proved Theorem 2. Right, so what we're going to do is show that A transpose times A inverse transpose is the identity matrix. Right, so we start. Since A is non-singular, right, we know that there exists some matrix, let's call A inverse, such that A times A inverse is the identity matrix. What we're going to do is take the transpose of both sides. What we get right from the property that we studied in a previous video, take the transpose of a product, you reverse the order of the product and take the transpose of each matrix. Now, the transpose of the identity matrix, in fact, the transpose of any diagonal matrix, is the same. Again, this is a fairly straightforward exercise to show this. We can use a similar argument to show that A transpose times A inverse transpose is also the identity matrix. Thus, we have just shown that A transpose is non-singular. We've shown it has an inverse. And its inverse is A inverse transpose. That concludes this video on types of matrices. Again, there was an extremely heavy emphasis on inverse matrices. Right? We had several properties that we proved about them. Other important matrices here, again, the square matrix and the identity matrix. In the next video in this series, we are going to take a look at systems of linear equations, particularly how we can solve a system of linear equations. And this should actually be a review from intermediate algebra. Our goal is to take now what we've just learned about matrices and see if there's an easier way of solving those systems using matrices. That is the goal for the next several videos. Until next time, have a good one, and I will see everyone in the next video.